In the previous videos, we have looked at the electromagnetic spectrum, the electromagnetic radiation, and even atmospheric windows. We have learned that the sun is the primary source of energy. The radiation from the sun travels all the way down to the earth, but not all radiation from the sun gets to the earth's surface. We have learned that some are absorbed. But you know what? Not all radiation is absorbed. Not all radiation gets to the earth's surface. As a matter of fact, a good portion of this radiation bounces off into several directions. And this is called scattering. In this video, we shall learn what scattering is all about, the various types of scattering, and the effects of these types of scattering, and how scattering is important in the field of remote sensing. Get ready as we learn together. Don't forget, this is Weathersphere. What is scattering? Scattering is the redirection of electromagnetic radiation by particles and molecules in the atmosphere. We have learned that there is the incident radiation from the sun, and when we have the incident radiation from the sun, there is what is called backscattering. These scattering agents are aerosols. When we talk about aerosols, we are talking about dust, smoke, and pollutants in the atmosphere. And another scattering agent is the cloud droplets in the atmosphere. And these cloud droplets comprises water droplets and ice crystals. We also have air molecules that serve as scattering agents. And these air molecules are majorly nitrogen and oxygen molecules. Now, we have the radiation that has not been absorbed, or the radiation that has not been scattered reaching the Earth's surface. We have various types of scattering. Number one is the Rayleigh scattering. The Rayleigh scattering is caused by molecules that are much smaller than the wavelength of the radiation. They are dominant in the blue wavelengths. Then we have the Mie scattering. The Mie scattering is caused by particles comparable in size to the wavelength. Examples of these particles are the aerosols and the cloud droplets. And after the Mie scattering, we have the non-selective scattering. This is caused by large particles, majorly clouds and dusts. These particles scatter all wavelengths fairly equally. Why is scattering important in remote sensing? Scattering is important in remote sensing because it affects signal strength and quality. Scattering also reduces visibility in many cases. Scattering influences atmospheric correction, and scattering is critical for accurate data interpretation. And so, while the atmosphere modifies radiation, the most important information comes from when the radiation actually gets to the Earth's surface. Right now, we shall look at Rayleigh scattering in detail. And just as I had said, Rayleigh scattering is the scattering of light by particles much smaller than the wavelength of light. So we have particles in the atmosphere, and we have measured some of these particles. Now, the scattering intensity is inversely proportional to the fourth power of the wavelengths. And we also need to know that the shorter wavelengths, that is, the blue and the violet wavelength of the electromagnetic spectrum, scatters more, while the longer wavelength, that is, the red and the orange components of the electromagnetic spectrum, scatter less. And this is why the sky is blue. Just as I had said, the blue light, that is, the shorter wavelengths is scattered much more strongly than the red light, which is the longer wavelengths. Once again, this is why the sky is blue. So in case someone asks you, what is the principle behind the blue sky? The answer is very simple. The principle is called the Rayleigh scattering. This is very important in remote sensing as it affects atmospheric correction, visibility, and interpretation of satellite and aerial imagery. Next up, we shall look at mite scattering. Mite scattering has already been defined as the scattering of light by particles comparable in size to the wavelength of light. And these particles comprises the aerosols, dust, smoke, pollen, and cloud droplets. And when we look at the scattering characteristics, it simply means that light or radiation is scattered in several directions, but more strongly in the forward direction. Unlike the Rayleigh scattering, there's a much weaker dependence on wavelength, and this has effects on the atmosphere. For example, it is responsible for the white appearance of clouds, for the appearance of haze, and the reduction of visibility due to haze. And so it creates the white or milky appearance of clouds and hazy skies. And this is very important in remote sensing because it also affects atmospheric correction, contrast, signal attenuation in satellite and aerial images. So the major impact of the mite scattering is that it reduces visibility, it affects the energy balance, and it influences the climate. Lastly, we shall look at the non-selective scattering. Non-selective scattering is the scattering of light by large particles. In this case, these particles are much larger than the wavelength of light, and it scatters all wavelengths of light nearly equally. So in this case, light is scattered in all directions with little dependence on the wavelength. That is why it is known as the non-selective or the wavelength independent scattering. This form of scattering is responsible for the white or gray appearance of clouds, fog, and haze. This is because all colors of visible light are scattered equally. And when this happens, in most cases, what you have is the white effect because the combination of all the colors in the electromagnetic spectrum gives you that white effect. The non-selective scattering is important in remote sensing as it strongly affects atmospheric path radiance, contrast, and signal attenuation in optical and multispectral imagery. In the atmosphere, it reduces visibility, it creates haze, and it increases sky brightness. The common sources of these large particles are cloud droplets, fog and mist, dust and smoke, and water droplets. Now that we know what atmospheric scattering is all about, and in the previous videos we have learned about atmospheric absorption and the atmospheric windows, we need to find out, so what happens when the radiation gets to the Earth's surface? What are the effects caused by the radiation that gets to the Earth's surface, and what are the importance? And that will lead us to the next topic called spectral signatures. You don't want to miss that for any reason. I hope we have learned something from today's presentation, and I hope that we'll get to study more and explore more. I would like to have your feedback on what you have learned and your questions, or any comment or remark you have to say about this presentation. Do well to drop your thoughts in the comment section right there. Don't forget to like and share and subscribe to this channel, and do well to turn on the notification bell so you can get regular notifications whenever a new content is dropped. Till I come your way in the next video, keep exploring, keep learning, and don't forget, this is Weathersphere.